Hello, this is a presentation I gave in Denver, Bob Miller's Toxicity Conference in September 2019. I'm going to be talking you through the slides that I gave there. So some of them aren't going to quite sync up, but it should be good enough. I think you'll find this information on nitric oxide and toxicity extremely interesting. First of all, if you have questions, just go ahead and write them in the comments below. I'll be circling back from time to time to check in and answer to the best of my ability. So first of all, thanks for tuning in. You know, we are creating all kinds of problems for ourselves, and it's people like you who are going to help us figure out how to get out of this problem. Every 2.6 seconds, a new chemical is formulated. And over the past history of humankind, about 50 million different substances have been used, discovered by us. It's really kind of incredible when you think about it. 80,000 of those are registered with the EPA. And about 2,000 new chemicals are added to that registry every year. Many of those chemicals, however, even though they're registered, they're not regulated. In 2016, the EPA embarked on an aggressive program to test the tens of thousands of unregulated chemicals currently on the market. They should be finished this program sometime in the next few hundred years. Are we doomed? Science has opened Pandora's box. And do you remember what the last thing to crawl out of Pandora's box was? If you remember your Greek mythology, you would remember hope. Science has got us into this chemical mess, and I believe you, with the help of functional genomic nutrition, is going to help us get out. In the next 90 minutes, I'm going to lead you through a 9-step process. Actually, it's a little shorter than 90 minutes. Because we've cut out quite a few parts from the live presentation here. So it's going to be more like 60 minutes, 65 minutes. By the end of this presentation, you're going to have some protocols to help deal with cardiovascular problems. And more importantly, you're going to understand the science behind the protocols so you can modify them for your most difficult patients. And my intention is that you end this presentation and hit the ground running. It's a pretty bold statement, but I think the information here is that good. For those of you who don't know me yet, my name is McKay Rippey. My training is as a 5-element acupuncturist. I've been in practice for 30 years and live on a small farm in central New York. My journey down the nitric oxide rabbit hole began 2.5 years ago when I had a reactivation of Lyme disease, and that left me unable to lift my right arm for 3 months. It was a miserable experience. However, I am grateful that gave me a lot of time to really dig into the power, purpose, and pathology of nitric oxide. But before we jump in, I need you to do one thing for me, okay? And that is don't drink the Kool-Aid. So what do I mean by that? I want this presentation to be like a wine tasting, except you're going to be sampling information instead of wine. I want you to sniff what I'm teaching, swirl it around in the glass, hold it up to the light, take a sip. Do that funny thing that wine tasters do with their cheeks, and then spit it out. If what I'm teaching is good, and I believe this information is very, very good, you'll want more. You will understand your most difficult patients in a whole new way, and you will have new tools in your clinical toolbox to help them. And that reminds me, conflicts of interest are no joke. I make a small bit of money on the supplements I recommend. And that's that. So, are you ready to jump in? Awesome. Let's go. So, toxins create all kinds of health problems, but we're going to focus on cardiovascular disease. Why? Because it's a huge problem, and you're seeing the effects of it in your office every day. According to the American Heart Association, every 40 seconds an American will have a heart attack. As of 2016, 28.2 million U.S. adults were diagnosed with heart disease. The Heart and Toxins is a really depressing 668-page read. It thoroughly examines many sources of toxicity and how those toxins affect the heart. This truly is the age of chemistry, and this age has a dark side. We could spend the rest of this weekend going over the toxins in this book, but I've chosen to focus on one, and that is bisphenol A, or BPA. A 2003 CDC study showed that 93% of people had BPA in their urine. And that makes me wonder about the other 7% if they don't have some sort of detox genetic variant that doesn't allow them to detox. Maybe they simply can't excrete the BPH. In addition to its well-known endocrine disrupting effects, this CDC links BPA to all kinds of health issues. And you can see that it's found in lots of everyday items. It's no wonder we all have BPA in our systems. This 2014 study from the Journal of the Federation of American Societies for Experimental Biology showed that BPA caused hypertension. Here are some of the highlights from the study. There's higher urinary BPA Higher urinary BPA concentrations are associated with arterial hypertension in humans. And they wanted to know why that happened, so they designed a study. They put BPA in the drinking water of 8-week-old mice for 30 days. The mice developed a dosage-dependent high blood pressure, and that's a strong indication that there is a cause and effect relationship. The reason they developed hypertension in the mice is they had a 1.7-fold increase in arterial angiotensin II, a 2.5-fold increase in calcium calmodulin-dependent protein kinase 2 alpha, and an 8.7-fold increase in endothelial nitric oxide synthase. Now that's huge. BPA increases the expression of endothelial nitric oxide synthase, or eNOS. The reason why that's huge is up till recently, eNOS was believed to be expressed at a fairly constant physiological level and didn't vary much. We now know that just isn't true. They also found significant eNOS-dependent superoxide and peroxynitrite accumulation. So that's also huge. And you might get tired of me saying huge during this presentation, but it's immensely important. So what that's showing is that the nitric oxide 3, the eNOS, the endothelial nitric oxide, is being overexpressed, and that it is being uncoupled, and instead of producing nitric oxide, is producing the oxidants superoxide and peroxynitrite. So are any light bulbs starting to go off for you like they did for me when I first read about this paper? Yes? No? It's okay if they aren't. We're going to unpack the details of what is happening in the study, and you'll see later that not only does blood pressure rise because of a lack of nitric oxide, but the stage is also set for significant inflammation and even tissue destruction by activation of the innate immune system. So the study concludes, our data suggests that BPA regulates blood pressure by inducing angiotensin II and calmodulin kinase 2 alpha uncoupling of endothelial nitric oxide. Clearly, BPA is a huge problem, but I don't want to get stuck on BPA. Instead of focusing solely on the toxin itself, we're going to focus on something which I think is far more important and far more universal. We're going to focus on how nitric oxide and its synthesis get disrupted. And I believe nitric oxide is disrupted in many of your sickest patients. There's no way to cover everything nitric oxide does in 90 minutes and do it any kind of justice. So during this presentation, we're just going to be focusing on the downstream cardiovascular damage from nitric oxide dysregulation. But we could just easily talk about Alzheimer's or Lyme disease or autism, autoimmunity, ALS, so forth and so on, insomnia, depression. The list literally is endless. Nitric oxide is involved in a vast variety of physiological symptoms. Okay, let's move along here. I got to skip some parts here that we did live. We did a nitric oxide test, the saliva test. So we're skipping over this part here. Let's see, where am I? Okay, deeper dive into peroxynitrite. So this is a 2007 study from Physiological Reviews. It's a fabulous paper on nitric oxide, superoxide, and peroxynitrite. It's open access. I highly recommend that you track this one down. So the name superoxide implies that superoxide should be a powerful oxidant. Superoxide, however, more generally behaves as a mild reductant under physiological conditions rather than a superoxidizing agent. This is because superoxide exists naturally as a small anion, which is more likely to surrender its electron than to accept a second electron from another biological molecule. However, superoxide is a strong oxidant when it's mated to a protein. That way it will directly oxidize positively charged chemical moieties such as iron sulfur centers. And I'm going to be digging into this more because I think this is super significant. I want to know exactly what proteins are getting charged up by superoxide and who they're chasing after. So the destruction of iron sulfur centers in mitochondria has been well described in superoxide dismutase knockout mice. Aconitase is another iron sulfur protein that is particularly susceptible. And aconitase is a step in the Krebs cycle. Let's see if we've got that slide here. There we go. So to review, superoxide, when it's paired with a protein, has a particular appetite for mitochondria. This is why superoxide dismutase and genetic variants in the production of that enzyme are such a big deal. Okay, let's move on to nitric oxide. Although nitric oxide is often described as a highly toxic and reactive molecule, it's not. In fact, inhaling low concentrations of gaseous nitric oxide is approved by the FDA for treatment of persistent pulmonary hypertension in newborns. In addition, nitric oxide can be produced for 80 years by neurons in the human brain without overt toxicity. Paradoxically, the production of the same molecule can become highly damaging to the same neurons within a few minutes during pathological challenges such as a stroke and infection. So how is this possible? The answer lies in our old friend peroxynitrite. The reaction of nitric oxide with superoxide to form the much more powerful oxidant peroxynitrite is a key element in resolving the contrasting roles of nitric oxide in physiology and pathology. A number of pathological conditions are associated with the simultaneous generation of nitric oxide and superoxide. Nitric oxide sources are restricted to the activity of the various nitric oxide synthases, whereas superoxide arises from multiple sources, including electron leak from the mitochondria, NADPH oxidase, xanthine oxidase, and the uncoupling of nitric oxide synthases. By the way, I think that part of the paper, the review, needs to be updated. I'd like to add that cytochrome P450 can reduce nitrite to nitric oxide, and so can other enzymes in the body under hypoxic or acidic environment. So there are situations where nitric oxide can be formed outside of the nitric oxide synthases. I think that's important to point out. So products like Berkeley Life Professional, where they're providing nitrate that eventually gets converted to nitrite, can up your nitric oxide levels. Okay, the next part of the paper is a bit long, but it's really the heart of the presentation. Yeah, I meant that pun. So sit up, take a few deep breaths, and get some oxygen into your brain. It's that important. Also, I don't have a lot of slides for this, so visually it'll be a little bit boring, but I think you can hang in there. So here we go. In 1990, the first papers suggesting that peroxynitrite could be a biological oxidant were published. Before then, most scientists did not believe that the body could produce something as toxic as peroxynitrite. In fact, some of the original ideas of nitric oxide and peroxynitrite came from the research into air pollution. At the time, much of the literature suggested that nitric oxide was simply a scavenger of superoxide and thus acting as an antioxidant. However, Joseph Beckman and his group at the University of Alabama, Birmingham, showed peroxynitrite exists in vivo and produces far more hydroxyl radicals than the widely accepted Fenton reaction. In addition, peroxynitrite produces nitrogen dioxide, which can lead to novel oxidation products that were previously only suspected to occur after exposure to cigarette smoke or to air pollution. So essentially, if your body's producing peroxynitrite, it's as bad as if you were smoking or out in the smog of a big city. And that's crazy. It just blows my mind that peroxynitrite can generate the same toxins that are in cigarette smoke. Just let that sink in for a moment. Separately, neither superoxide nor nitric oxide is particularly toxic in vivo because they are efficient means to minimize their accumulation. Superoxide is rapidly removed by high concentrations of scavenging enzymes called superoxide dismutases, and there are distinct isoenzymes located in the mitochondria, the cytoplasm, and extracellular compartments. Nitric oxide is rapidly removed by its free diffusion through tissues and into red blood cells, where it is rapidly converted to nitrate by reaction with oxyhemoglobin. This limits the biological half-life of nitric oxide in vivo to about a second, whereas concentrations of nitric oxide can persist in vitro for an hour. So that's the paper saying in a nice scientific way, all you in vitro studies that show nitric oxide existing for long periods of time are just plain wrong. Who said research was boring? All right, I'm going to pause and take a sip here, a sip of water. Okay, back to the research. When both superoxide and nitric oxide are synthesized within a few cell diameters of each other, they will combine spontaneously to form peroxynitrite by a diffusion-limited reaction. What that means chemically is every time nitric oxide and superoxide collide, they form peroxynitrite. The incredible speed of peroxynitrite formation is an important part of its effect, and no enzyme is required to form it. That fact will be obvious to the biochemists listening to this because of the nature of diffuse limited reaction, actually the definition of diffusion limited reactions. An enzyme cannot possibly catalyze a reaction as fast as nitric oxide and superoxide react all by themselves. In fact, nitric oxide is the only known biological molecule that reacts faster with superoxide and is produced in high enough concentrations to outcompete endogenous levels of superoxide dismutase. So what that means under normal conditions, if it's a choice between nitric oxide and forming with superoxide and making peroxynitrate, or superoxide getting cleansed from the body by superoxide dismutase, the nitric oxide is going to win out every single time and make peroxynitrite. That's huge. So if you have lots of nitric oxide being produced anywhere near the source of superoxide, and sometimes that's happening in the same cell, all the superoxide dismutase in the world is not going to stop the formation of peroxynitrite. Consequently, the kinetics and the thermodynamics of the reaction of superoxide with nitric oxide make the formation of peroxynitrite inevitable in vivo. It's not a question of if you're making peroxynitrite, but how much. So let's look into that. This is what you would expect as the equation of nitric oxide plus superoxide to make peroxynitrite. So as an example, 10 right-hand gloves plus 10 left-hand gloves equal 10 pairs of gloves, right? It should be that simple. However, right, we're dealing with biochemistry here. Nothing's ever simple. However, because all of the biological reactions that peroxynitrite triggers downstream, you get this. A 10-fold increase in nitric oxide and superoxide gives a 100-fold increase in peroxynitrite. So when the immune system is activated, nitric oxide and superoxide levels can increase by 1,000-fold. That gives rise to a 1,000,000-fold increase in peroxynitrite. Not 100-fold, not 1,000-fold, not 100,000-fold, a 1,000,000-fold increase. And that's just bigger than use. It's a game-changing biological shift. So is it any wonder why some of your patients are struggling? Is it any wonder they're inflamed? Is it any wonder they cannot handle anything that might cause even the slightest bit of inflammation? I had a patient once who couldn't eat without having a massive inflammatory storm. So now I understand what she was going through a whole lot more. You know, we've talked about endothelial nitric oxide, but we really haven't gone over what the endothelium is and what it's doing. So here, let's just briefly cover that real quick. So here's a diagram, and I don't know if you can see that in this recording or not. No, it's just going through the thing. So sorry about that. Let's back up. I was hoping I could draw on this. Let's see, where are we? Okay. Back to the slide. So here is a diagram of a blood vessel. So in the middle, those little peach-colored things, those are red blood cells. And then you'll see a layer of the endothelium, and then on either side, either above or below those bigger cells, those are the smooth muscle cells. So the endothelium serves as a barrier and a sensing mechanism. And that's really enough to know for this lecture, this video that we're putting together. There's so much more that the endothelium is doing. But that's its job. It's to create a barrier and to sense what's going on inside the blood vessel and to communicate that to the entire system. We talked about what nitric oxide is doing, but what's really important to understand is how far these chemicals can diffuse outside the source cell where they're generated. So what you see here is nitric oxide can diffuse really freely throughout cells, and unless it bounces into something it's reacting with, mostly a heme. So if it goes into the bloodstream, it's going to react with the platelets there and react with hemoglobin and to form nitrate. And that gives its half-life of about 1 second. So it can easily diffuse through several cell diameters, no problem. All right, next, let's look at superoxide. And there you can see superoxide doesn't travel so much, and that's really due to the fact that there's so much superoxide dismutase around, right? There's superoxide dismutase inside the mitochondria, inside the cell, and even outside in the extracellular space. So there's lots of superoxide around to mop up superoxide. However, just as we mentioned before, if nitric oxide gets there before the superoxide, or they're there at the same time, the superoxide will react with the nitric oxide to form peroxynitrite, and that's what we'll look at next. Peroxynitrite, even though it gets formed so incredibly quickly by the chemical reaction, it can diffuse quite a bit, and that's because it reacts selectively. It isn't, even though it's a radical and a strong oxidant, it doesn't just react with everything around it. So it can bounce around from cell to cell for a while before it finds a site that it wants to react with. And last, I think it's really important to have a look at the other really well-known radical, the hydroxyl radical. And here you can see how tiny its diffusion radius is. And that's simply because it is so very reactive that it doesn't travel anywhere. So the ability of the hydroxyl radical to travel is about the diameter of a small protein, and that's 10,000 times less than peroxynitrite travels. So they're just radically different. Even though we call them free radicals and talk about oxidative stress in this kind of general blanket terms, I think it's really, really important to begin distinguishing the difference between these radicals and what they're doing and what their potential are. They are not the same. You can't not treat them the same. They're radically different based on how quickly they're formed, A, and then how quickly or how far they can diffuse, B, and then C, what they're reacting with. So a hydroxyl radical just reacts with everything and oxidizes anything in its path. It's so reactive it cannot travel at all. So the contrast between peroxynitrite and hydroxyl radical is dramatic. The hydroxyl radical is formed by a rather slow chemical process via the reaction of ferrous iron with hydrogen peroxide, but reacts so quickly with everything around it that it can only diffuse about the diameter of a small protein. In contrast, peroxynitrite is formed very, very quickly each time superoxide and nitric oxide collide. However, it reacts more slowly and more selectively throughout the cell. That makes the biological and pathological implications of peroxynitrite far, far more interesting because it can have a more subtle and more specific action in and around the cell. So one of those reactions I've discovered recently, and it was interesting to hear Dr. Joseph Mercola bring up the same fact here. We're kind of on the same page as far as nitric oxide goes. And that is when you combine peroxynitrite and carbon dioxide, and there's plenty of carbon dioxide in the cells, right? It's just part of the oxidative process within the mitochondria. You get a curious molecule called the carbonate radical. And I'd like to introduce you to a new radical if you've never heard of this before. And it's particularly damaging to DNA. So peroxynitrite forms another radical that goes out and clobbers DNA. Isn't that interesting? This 2001 study from the Journal of Biological Chemistry shows that the carbonate radical is particularly good at oxidizing guanine proteins in DNA. Man, peroxynitrite is the gift that keeps on giving. It's just crazy, isn't it? And have you noticed something here? All these radicals are so much different from each other, and they behave in so much different ways. We need to stop thinking of them simply as oxidants or part of some vague term like oxidative stress. They each have unique personalities. A hydroxyl radical does not behave anything like superoxide. Superoxide behaves nothing like nitric oxide, and nothing can keep superoxide and nitric oxide apart from each other. And peroxynitrite has its own peculiarities, like its exponential multiplying effect, and its ability to generate a whole host of other oxidants, including our new friend, the carbonate radical, which has its own idiosyncrasy of gobbling up guanine in DNA. Our success as practitioners will only be enhanced as we begin to tease out these differences. So back to the 2007 paper from Physiological Reviews. They say once a flux of nitric oxide and superoxide is produced simultaneously in close proximity, the generation of peroxynitrite is considerably enhanced. Peroxynitrite-dependent cytotoxicity is then mediated by a myriad of effects including lipid peroxidation, protein nitration and oxidation, DNA oxidative damage, and activation of matrix metalloproteinases, and the inactivation of various enzymes. Mitochondrial enzymes are particularly vulnerable to attacks by peroxynitrite, and this leads to reduced ATP formation, mitochondrial swelling, and weakening of the outer mitochondrial membrane. So this allows for the efflux of several pro-apoptotic molecules, including cytochrome C and apoptosis-inducing factor. So in addition to its damaging effects on mitochondria, peroxynitrite can inflict mild to severe oxidative injury to DNA, resulting in DNA strand breakage. That's bad news. This in turn activates the nuclear repair enzyme PARP. Activated PARP consumes NAD, And, I don't have time to go to NAD, but it's all over the internet, and it's the kind of the supplement of choice these days, nicotinamide, riboside, and so forth and so on. But NAD is usually important. So anyway, back to the paper. Mild damage of DNA activates the DNA repair machinery and normal cell functions. So if there's only a little bit of peroxynitrite, the body can handle it. However, once more peroxynitrite is produced and moderate oxidative and nitrosative, oxidative and nitrosative stress-induced DNA damage occur, the cell may be retired, broken apart, and recycled by the apoptosis process. And if even more peroxynitrite is produced and massive damage occurs, the orderly process of apoptosis fails to keep up and you get necrosis instead of apoptosis. That's bad news. In this last scenario, PARP is overactivated. That's the DNA repair enzyme. So it's overactivated. Massive amounts of NAD are consumed, and cellular ATP production collapses and is released into the extracellular matrix. So that's what that chart there is showing. It's the whole peroxynitrite damage to the mitochondria and what can occur with that. So once cell death by necrosis kicks in, it can be very difficult to stop. Septic shock is the classic example, but I think many of our sickest patients are flirting on the edge of an apoptosis/necrosis crisis. So I'm going to go out on a limb here with this hypothesis of mine. I believe we have to go beyond the good and bad paradigm of the redox system. Simply, antioxidants are good, free radicals are bad. Why does the body make peroxynitrite? It's a good question, right? Is it a mistake? I don't think so. So peroxynitrite is biphasic. Physiological amounts mediate apoptosis. Apoptosis is an immensely important process. The orderly retirement of cells recycles proteins and lipids and prevents runaway inflation. On the other hand, large amounts of peroxynitrite is part of the innate immune system and mediates cell death by necrosis, which targets both pathogens and host cells. So it can take 4 to 7 days for the adaptive immune system to react to a novel pathogen. And if you didn't have a robust innate immune response, you would just die. So peroxynitrite is an important molecule. The problem is peroxynitrite production can spiral out of control, mostly because of the exhaustion of antioxidant enzymes. But genetics can also play a huge role in that as well. So once that starts, it can be super hard to stop. Are the light bulbs starting to go off yet? Have I blown your mind? Yes? Okay. So this part of the lecture that I gave, we had Mark Young from Zona Plus give us a demo of his device. It's kind of cool. Go to zona.com and check it out. Essentially, it can reduce blood pressure by about 20 points. That's the average number in all the studies they've done, simply by squeezing this device for 6 weeks. If that ain't mind-blowing, nothing is. So we're not going to pause here and do anything about Zona. Just visit their website if you want to know more. So we're going to move along, and I want to introduce you to Team Nitric Oxide. So the first member is nitric oxide synthase 1, or neuronal NOS, and it's primarily found in the nervous system, but not exclusively, and that's important. Unfortunately, the naming of these enzymes kind of gives the idea that they only show up in certain tissues. They're not that exclusive. Second is NOS2, or inducible nitric oxide synthase. And again, the idea with the name is it only happens when the immune system is activated. We now know that's not true. The last enzyme, NOS3, or endothelial nitric oxide synthase, is the vasodilating enzyme, right? It reacts particularly to signals from the blood pressure system to regulate blood pressure, how tight or loose the vessels will be. However, again, there's more endothelial NOS in the muscles than there is in the endothelium. So go figure. Don't get hooked on the names. You just need to know them when you're reading the material. And the other thing, they go back and forth between NOS1 and neuronal NOS, the different names. So just memorize them and then you'll be fine. You won't get confused reading the papers. I had to look them up probably for the first 6 months. I get turned around, especially late at night, reading the papers. Okay, so there's more. We have 2 more team members. There's the nitrate-nitrite pathway. And this is fascinating because we eat nitrates in our food mostly, but you can take them in supplement form too. So green leafy vegetables primarily. The nitrates get concentrated in your saliva. And then there's bacteria on the root of your tongue which converts it to nitrate. Humans do not have an enzyme to convert nitrate to nitrite, so we rely on bacteria to do that. Once the nitrite is present, we swallow it again, and the acidic environment in the stomach turns it immediately into nitric oxide, and that's pretty cool. So the nitrate can get transported through the body. There are several enzymes, especially in hypoxic conditions, that will convert the nitrite into nitric oxide where it's needed. The last pathway or physical pathway, so these are things like UVA radiation, so sunlight, exercise increases nitric oxide. The Zona product does that. There's special breathing techniques. I'm sure there are a bunch of other things that we can do physically that increase our nitric oxide expression. So that is Team Nitric Oxide, and I think it's important to know the 5 players. There are probably others, and as they get discovered, we will add them to the team. Okay, so let's take a closer look at the genetics and the enzyme side of things. So just a quick review. Remember, the enzymes are NOS1 or neuronal nitric oxide synthase, and this is calcium dependent. So neuronal NOS will not make nitric oxide unless the level of calcium in the cell is sufficient. Inducible nitric oxide is calcium independent. So when it is created, when the DNA gets triggered and the enzyme is expressed, as long as there's a calmodulin bound to it, it doesn't need the calcium. So this cranks out nitric oxide as a much higher level at the micromolar amount, whereas the calcium-dependent enzymes only produce it in the nanomolar amount. So that's about 1,000 times different. So the nitric oxide synthase 2, the inducible nitric oxide, will produce about 1,000 times more nitric oxide than either NOS1 or NOS3. And there's our endothelial NOS. And that's really, really important because, 1,000 to 1, yeah, that seems like a big number. But let's say you have 5 enzymes, right? So now all of a sudden the number is 5,000 compared to 5. The numbers start stacking up very quickly once you start doing the math. Okay, let's move along here. I've got to find my place in my notes here. NOS2, NOS3, good. And the next section is based on 2 papers, a 2019 article from Nitric Oxide and this 2013 article from the American Journal of Heart and Circulatory Physiology. So we're going to talk about the nitric oxide synthases, the enzymes, and they all share these common traits. So this covers all 3 versions of the enzymes, even though it says there in the heading that this is NOS3. This holds true for NOS2 and NOS1 as well. So all nitric oxide synthases start off as a monomer with the reductase domain and an oxygenase domain. Don't worry if you don't understand the biochemistry. They just mean there are different things going on in the different parts of the enzyme. Zinc thiol and heme allow 2 of these monomers to combine to form a homodimer. And all homodimer means is there are 2 monomers connected together, right? Homo meaning the same, dimer meaning two. So two of the same, two of these nitric oxide synthase monomers hold hands, and that's when they become active. I failed to mention that going back, that the monomer is inactive. It doesn't produce nitric oxide. Once it's joined with its buddy, then it can begin producing nitric oxide. And it's important to know that that zinc cluster is there at an important binding site, and the BH4 helps keep these monomers connected, the homer dimer intact. So when BH4 starts having problems, the whole system breaks down. All right, so here is what we've got. This is the electron transfer. So NADPH drops off an electron. It gets transferred down the redox domain. And actually, that's not the right term. Where am I now? It's the reductase domain. There we go. Okay, I had to look that up. Blank there for a second. So the reductase domain from FAD to FNM. And you can see there that third red dot there, the CAM/calcium 2 plus. That's the calmodulin calcium molecule there. So without that there, the electron transport doesn't happen and the enzyme shut down. So that turns things on. The electron gets passed all the way to the opposite side of the enzyme, to the heme section, and there arginine gets oxidized. So this is an oxidized heme complex. It in turn oxidizes the arginine, and that is what makes nitric oxide, and as a byproduct, citrulline as well. So here is the chemistry behind it. So it takes 1 hydrogen, 2 L-arginines, 3 NADPH molecules, and 4 oxygens. And in turn, what's produced by this enzyme are 4 water molecules, 2 L-citrulines, 3 NADP plus, and 2 nitric oxide molecules. So that's what's going on in an enzyme. Now, we've all heard a ton about uncoupling, and this is what is going on. So uncoupling is a technical chemical term, but all you need to know is that uncoupling means the enzyme is producing superoxide, not nitric oxide. So the first way that this happens is L-arginine is not available. Now, there's some discussion about whether or not this can happen. And in fact, I'm here to tell you it can. So what happens is there can be plenty of arginine in the blood supply, so the tests come out normal. There can even be enough arginine within the cell, but it's being sucked away. The gradient isn't close enough to the nitric oxide synthase, and this heme, this red heme, oxidized heme that does the work in the enzyme, isn't stable enough, and it falls apart. So when the arginine isn't available right there, right on time, what happens is the oxygen in the heme domain create a superoxide radical instead. Now, what is going on there is in the literature referred to as the arginine paradox. However, I just like to call it the arginine steal. And the primary culprit in the arginine steal is arginase. Now, arginase is produced a lot when the immune system is tilted toward the Th2 or macrophage 2 immune response. So when the immune system gets polarized to that, that's essentially the healing phase. That's a little oversimplified, but basically the healing phase of the immune system. On a larger level, the liver urea pathway can consume a ton of arginine, and this can affect the nitric oxide synthase 3, the endothelial NOS. It's not simply something that's going on with the inducible NOS and the immune cells. All right, so that's the first method of uncoupling I want to talk about. Now there's a second uncoupling that happens, and this involves the BH4 molecule. And you'll see there are two recycling circles next to the BH4 to the right of it, and in between there's, the BH3 and a ascorbate. So as BH4 donates an electron to this process, it becomes a radical called BH3. And as long as it is reduced back to BH4, there's not a problem. Ascorbate, which is a bioactive form of vitamin C, enables this to happen. Now, this is the very, very, very important role of BH4 in nitric oxide production. So as we talked about earlier, up to the top left in the reductase domain, the NADPH donates the electron. Now, this electron, in terms of chemistry, biochemistry, moves down to the opposite side slowly. And if it doesn't happen fast enough, the heme doesn't stay stable and spits out the superoxide. So BH4 is there to temporarily lend an electron. So as long as the BH4 is there, the heme is stable enough, long enough to oxidize the arginine to citrulline. And then what happens if the BH4, after it donates its electron, isn't able to recycle and it gets stuck at BH3, then the arginine, doesn't matter how much is there, the arginine can't get oxidized. It can't get transferred there to the site in the enzyme that makes this all happen fast enough, because the heme is so unstable in its ferrous state, in this oxidized state, that it spits out a superoxide. So just like with the other case with the arginine. This case, though, the arginine's right there, but the heme is so unstable it can't reach out and grab the arginine. That's the BH4 NOS uncoupling. So to recap, we've got the arginine steal when there's no arginine available. And then we have BH4 deficiency. So sometimes there's just not enough BH4 being made by the body with certain deficiencies or pathway deficiencies there. In this case, the nitric oxide synthase homodimer isn't going to be formed or stay formed long enough to make enough nitric oxide. So in these cases, we can see a very low level production of nitric oxide. The other thing that happens is there's a lack of reduction capacity inside the cell. Essentially, the cell can't keep up with all the oxidative stress, and the nitric oxide synthase starts to fall apart and produce superoxide instead, right? So that's the uncoupling. And we know now, because of what we've been looking at, that when you've got the superoxide being produced next to nitric oxide, imagine if one cycle the enzyme's producing superoxide and then kind of recovers a bit and then produces nitric oxide, they're going to combine immediately, right? And form a peroxynitrite. That's bad, bad news. All right. So we're entering the home stretch. You've done a great job so far. Hang in there. We're going to bring this all home. You know, when I first talked to Bob Miller and he invited me to present at his conference, he said, can you do this in an hour? I said, no problem. Then I started doing some more research and I called him back and said, Bob, I think I need another half hour. All right. Let us look at this mouse study. It blew my mind. It was a 2009 Japanese study. It was published in the Circulation Journal. And it's open access, so take your time. This is well worth reading. This is where I got the concept of team nitric oxide. This study shows that nitric oxide synthases work in tandem and will compensate for each other. All right, here is a graph showing basically how many of the mice died. So the red stepped at the bottom is the worst case, and the other cases are not quite as bad as you can see. So what they did was they're trying to find a mouse model to mimic human heart disease, particularly heart attacks. So they started out by taking out the nitric oxide synthases, genetically knocking out, then they started with endothelial loss. So they started knocking out one enzyme at a time, thinking, okay, which one of these is most important? So they started with eNOS. And when they knocked out one nitric oxide enzyme, they weren't getting the model they were looking for. So they started deleting two enzymes at a time with the various combinations. And that was a little more what they were looking for, but it wasn't until they took out all three nitric oxide enzymes that the mice started having heart attacks in the same way that human beings do. It's just crazy. So what they learned from this is that the NOS enzymes work together as a team and compensate for each other. So this is huge, right? You can't pigeonhole one NOS enzyme as only having one effect. Don't make that mistake. Somehow there's crosstalk going on between the enzymes, and they work together to maintain nitric oxide levels. So if you have a patient with heart disease and you're looking at genetic SNPs, you can't just assume because they don't have eNOS SNPs, right, NOS3 SNPs, that they're okay. You also have to look at the other NOS enzymes as well. So what you see here is cross-section of the mouse hearts. On the left is the wild type. You can see how nice and clear it is. And there's the cross-section of the coronary artery. It's beautifully open. On the right-hand side, what you see is a heart from a mouse that had all three nitric oxide synthases knocked out. That's the triply knocked out NOS mouse. And the blue in the top part in the heart, that's all necrotic tissue from the heart attack. And down below, what you'll see, it's the same type of coronary artery, but you can see the blue is fibrosis, so the body's trying to repair damage being done. And then you can see all the narrowing going on there, right? That artery is really blocked up, and that's because of tissue regrowth after all the damage being done. All right, so this is a graphical abstract of what the study found. So basically, a defective nitric oxide synthase system activates the renin-angiotensin system. And if you remember back to the beginning when we were talking about the BPA study, right? BPA also activated the renin-angiotensin system. So a lack of nitric oxide or a toxicity has the same effect. That's, to me, is mind-blowing. So we know with this first box here, the vascular dysfunction, that's going to happen without enough nitric oxide, right? That's a given. These other things, though, I found were super fascinating. And the next is when we don't have enough nitric oxide, there's not enough of a hormone called adiponectin. And adiponectin is produced by our fat cells. And there is a fat layer around the blood vessels, probably as an energy source, but it also produces nitric oxide. There is endothelial nitric oxide in these fat cells as well. And obviously these fat cells are sending out hormones and talking to the rest of the system here. So when there's not enough adiponectin, we know this is greatly involved with metabolic syndrome. So not only are you getting metabolic syndrome because of the activation of the renin-angiotensin system, but you have low adiponectin, and that's contributing to it as well. So it's no wonder that your patients are obese, struggling with blood sugar, struggling with hypertension, all those metabolic syndrome symptoms that we see day in and day out. The next thing that they saw with the triple knockout mice is there's higher levels of LDL, right? That comes as no surprise. But also with this chart, you get the idea that simply a strategy of lowering LDL is not a good idea. So if you're still stuck on the cholesterol paradigm of heart disease, it's time to move away from that. And last, this was super crazy fascinating. Without nitric oxide controlling and downregulating mast cells, the mast cells began to invade the heart, and they led to coronary spasms, and that was one of the triggers for the spontaneous myocardial infarction. So it's just crazy how much nitric oxide plays into all these systems, right? And when you take away nitric oxide, it's like taking away gears on a mountain bike, and eventually the body gets to a condition where it just can't compensate, right? All right, so let's go a little bit deeper into the pathways that get dysregulated with nitric oxide nitric oxide synthase dysfunction. So we're going to put this all together. Okay, here we go. So this time I'm only going out a little bit on a limb, and all this information has come from the studies we've looked at, but I put it together in a slightly different way and included a couple different things. And I think it's going to really bring this all together for you and help you make sense of it. We're going to build a chart. So first thing, and this has got zero, controversy to it. So at the bottom, we've got NOS3, endothelial NOS makes nitric oxide, right? No, that's right. We don't have to argue about that at all. And above it, we know that nitric oxide downregulates mast cells, and it downregulates NOX1 and NOX2, if not the other NOXes as well. And the NOX enzyme is the NADPH oxidase. And NADPH oxidase, its only job is to make superoxide and is triggered as an immune response. Okay? So that's our starting foundation here. Now, we learned from our first study that BPA increases angiotensin II, and not mentioned in that study, but from other studies, angiotensin II boosts the NOX enzyme. So that creates more superoxide. So we've got a major source of superoxide here. We also know that nitric oxide is being made. So when you put superoxide and nitric oxide together, you get peroxynitrite, the dreaded oh no chemical. Its chemical shorthand is oh no. And that peroxynitrite it downregulates BH4, right? It causes problems with BH4. And BH4 can get oxidized to BH2 or BH3. I put them both in there because if the BH4 is oxidized all the way down, one more step after the BH3, it becomes BH2 and has to go somewhere else to get refurbished, so to speak, to be reduced back to BH4. And this all leads to the NOS uncoupling. Remember that study and those charts that I showed you about NOS uncoupling. So once the uncoupling is happening, that leads to more superoxide and a reduction in nitric oxide. So once the nitric oxide synthases are uncoupled, what you're going to see is more superoxide and less nitric oxide. Bad news for your coronary system. Now, if there's not enough nitric oxide, what happens eventually is that the mast cells and the NOX enzymes are no longer regulated. Particularly when the NOX enzymes get going like crazy, they start something called the NADPH steal. This is Bob Miller's term. And we need NADPH for all kinds of reactions in the body. NADPH donates an electron in so many different pathways. It's critically important. So if it's getting burned up by the NADPH oxidase, the NOX enzymes, then you don't have enough NADPH to go around. In fact, what Bob Miller talks about is that NADPH, one of the emergency pathways for making NADPH is the body will take tryptophan to create NADPH. And when that happens, then you start getting wired and tired, right? Okay. And when mast cells aren't regulated, you get excess histamine dump, you get mast cell activation. And interestingly enough, histamine upregulates NOS3. So here you have uncoupling happening of the NOS. You have an increase in the NOS, right? And we showed here that the BPA increases NOS 8.7%. Now you've got, I'm sorry, not 8.7%, 8.7-fold. You've got histamine increasing NOS. So some of that is producing some nitric oxide, but it's uncoupled as well, right? So it's also producing lots of superoxide. So this is just a peroxynitrite machine going on there. And we know that the peroxynitrite also, when it meets up with the carbon dioxide, it makes a carboxyl radical. That leads to DNA damage. And once the DNA damage happens, we get the PARP activation, more NAD depletion. So we got the NAD steal going on, the NAD depletion, which is also a form of the NAD steal. This leads to necrosis. And necrosis, those of you who know, is a massive, massive inflammatory trigger. So when the body senses proteins that shouldn't be in the extracellular space, it gets very excited and pays attention and sends the innate immune system to go take care of business. And that causes a massive inflammatory cascade. And again, septic shock is the classic example of that, where it spins out of control. But in this case, what we're talking about is damage done to the heart disease. You can see here that between the histamine and the inflammation and damage done, that there are huge problems. So my bet is that you have many patients coming into your office where their hearts and coronary arteries look something like our poor mice here. All right, let's review this. Toxicity, NOS uncoupling, peroxynitrite, DNA damage, mast cell dysfunction, the NAD/NADPH steal, and cardiovascular disease. That's essentially what I've shown you, right? That's, if we could sum up this video in one slide, that would be it. But it was important to take you on the journey to get here. They're all related. Can you see that now? So the toxicity causes NOS uncoupling. NOS uncoupling causes peroxynitrite. That causes DNA damage. The peroxynitrite also lends itself to mast cell dysfunction, the lack of nitric oxide included in that. It also leads to the NADPH steal because the NOx enzyme's going nuts, and that's going to reduce the efficiency of the nitric oxide synthase as well, because there's not NADPH to donate the electron. And all this bundled up is creating cardiovascular disease in your patients. Now, the other thing is, I'd like to say that NOS uncoupling is such a misunderstood term, and it doesn't really have the emotional impact. So I would like to call this whole thing the nitric oxide steal. So not only is peroxynitrite being formed, but it's stealing nitric oxide. So you've got this explosion of inflammatory process. You don't have enough nitric oxide. Everything just goes haywire. All right. Call a friend. Tell them about this exciting news you have. I know you're thinking about a patient that you can help with this. So let's look real briefly at protocols. And in these protocols, we use all of the nitric oxide team, and we're going to put some gears back on your bike so you're going to be able to help your patients. All right. The first is basically what I call an anti-aging support protocol. And that's because as we age, our ability to produce nitric oxide diminishes. So if you have any concerns at all about this, and I think everybody should, these are the three products I recommend. NOS Activate, which I developed. Berkeley Life, which is a nitrate pathway, nitric oxide support. And H2 Infuse. And H2 Infuse supports both the Berkeley Life and the NOS Activate, and also has the additional capacity to scavenge up peroxynitrite, which is awesome. So the first ingredients in the NOS Activate, and this is the supplement that I made, that I designed specifically for the Toxin Conference and to support the nitric oxide synthase pathways. We've included some vitamin E, and this is designed to support the BH3 reduction of BH4. So in addition to ascorbate, we know that vitamin E can also help reduce BH3 back to BH4. Then we've included the cofactors for the NOS enzyme, the FAD, FNM, precursors, and zinc, which was so very important. The next, and we did talk about this a lot in the presentation, I didn't have time to squeeze everything in. We support the citrulline pathway, and this is to avoid the arginine steal. So if we support citrulline, citrulline gets recycled back into arginine, but it gets done so close to the nitric oxide synthase enzymes that the arginine steal isn't nearly as much as a problem if you just give arginine itself. And the last thing we've included in here is a pomegranate extract, and that's because it has gallic acid, and gallic acid is an excellent scavenger of peroxynitrite. Now, the Berkeley Life Professional product has vitamin C, and that supports nitrite to nitric oxide conversion, some thiamine, and that helps support enos, as well as B12, which is an important part of the methylation cycle, and that supports BH4 production. And then they include some magnesium and potassium that helps with the function of the endothelial and the smooth muscle around the endothelium. And last, their source of nitrate. They have a little bit of beetroot extract there, but they also have inorganic nitrate in case your patients have a problem with oxalates. And the last is the H2 Infuse from Bob Miller, and this is a molecular source of hydrogen. So you just drop the tablet in a glass of water, let it dissolve and fizz for a little bit, and then you drink it down, and you're getting a couple grams of hydrogen that way. It's an awesome product. So to recap, that's our anti-aging protocol. Next, when somebody has hypertension, we've added a few things here too, right? So obviously there's the foundational support, which we just talked about. And then I recommend adding the Zona and a specific supplement for the NOS3 enzyme. So even though they work as a team, NOS3 is predominantly the main enzyme in the endothelium. So we want to support that, excuse my S's there, support that specifically. And the last is we want to get the toxins out, the BPA out. And the plastic detox is a great product to do that from PHP. So let's look at my supplement, NOS3 Assist. So it starts with folate and folic acid, and just a little bit here. You can see it's just in the microgram amounts, not too much. And we did both sides because we didn't want to push methylation either too high or too low. And that activates enos. The next is a little bit extra potassium and magnesium. So this works together with the Berkeley Life product. And what would happen is you take the Berkeley Life first thing in the morning, and then you take the NOS3 Assist in the afternoon at lunchtime and also at dinner. And next we added in some Lowat. And Lowat supports adenopectin. And we talked about that in that one study. I don't know if anybody else who's supporting nitric oxide through this pathway. I think it's really exciting and it's going to have a lot of good effects for your patient. And finally, garlic and camu, which is a source of vitamin C. We've put these together. There's an excellent study that came out of the University of Albany, and they showed that these two, the garlic and the vitamin C, work synergistically together and much better together than singularly. All right. And I know you didn't get to hear Mark's presentation, but just go on over to Zona.com and see what they have to say. It's got a money-back guarantee. You can't go wrong. So this device regulates your blood pressure. And the study shows 6 weeks in, and your blood pressure drops significantly. It's mind-blowing. So it has an app. You plug it in, you sync it, you can track your blood pressure and how often and how well the Zona is working. So it's a great way to gamify things and keep you interested and keep you on track so you're using the device properly. It supports the nitric oxide pathways clearly by the drop in blood pressure that occurs. And last, as I mentioned, it does have a 90-day money-back guarantee. So what's not to like? Now, for my work with Lyme Ninja Radio, when I interviewed Mark for that show, he offered a coupon code that saves you $100 off the price. And that coupon code is my name, McKay, M-A-C-K-A-Y. So if you're going over to Zona.com and decide this is something you want to try, use my name as a coupon code and I'll save you $100. All right, last is the PHP, Plastic Detox 2. It's a homeopathic remedy, and it's designed to help the body in removing harmful plastics. So you can see here a list of the homeopathic levels that plastics that are included in this homeopathic remedy, and you can see there that BPA, bisphenol A, is included there. All right, so this is, once again, the hypertension protocol for those people who are struggling with hypertension. Either they want to get off the meds or the meds aren't working well, right? I have a ton of clients where the meds just don't do them any justice. Now, there's also going to be a group of patients that you have that are really, really struggling, right? So these are the people who have a stroke, right? Serious arrhythmias, coronary artery disease, so forth and so on. They're really much more inflamed, much more sick. Also, you may find they have significant genetics. If you do Bob's work with functional genomics and look into that, you'll find that they have SNPs in the NOS genes, glutathione pathways, BH4, de novo synthesis pathways, as well as recycling pathways, citrulline pathways, so forth and so on. It can create all kinds of problems and serious cardiovascular disease. Now, this is where you'll find those different gene pathways in Bob software. If you don't know Bob software, check it out. It's functionalgenomics.com, or leave a comment in the section below, in the comments below, and I'll get back to you on how to get hold of that and how to get started with the software. It's awesome. If you're not using this tool clinically, you need to be. But those are the different pathways I listed there and what you need to be looking at in terms of peroxynitrite production and in terms of nitric oxide function. It's not simply the NOS genes. It's not that simple. And just as a reminder, make sure you're looking at the details, because sometimes the details can be hidden within there. So if you need to go all the way to the gene analysis and take a look at the individual SNPs. All right. So for people who have serious cardiovascular disease, I've created a protocol I call the Cardiovascular Rescue Protocol. It includes everything in the blood pressure protocol, plus one important addition, and it's a supplement I put together. It's called NOS Defend, and this is powerful medicine, right? I shouldn't say medicine, I'll get in trouble, right? It's a powerful supplement. So the ingredients in the supplement are designed to free up nitric oxide synthase so it can return to physiological normal levels. Now, I'm not claiming it does that, but that's the intention of it, right? And how we do that is we suppress the arginase enzyme with rhubarb. So we stop the arginine steal and we shut down the arginase enzyme. And this allows the nitric oxide synthase to recover, right? It stops making peroxynitrite, which oxidizes the whole system and breaks down the nitric oxide enzymes. Next, we add in resveratrol, and that has great antioxidant properties, and it also inhibits the COX enzyme, which also produces some superoxide, as well as the NOx enzyme as well. So the resveratrol also dampens down the enzymes that make superoxide. And I think I may have misspoke on so the arginine is just the arginine steal, right, which creates the uncoupling of nitric oxide. So that's how that works on the previous one there. All right, the next ingredient, bicalin, and that inhibits arginase as well. And the last piece is berberine, and we all know this has great metabolic functions. Lots of people use this for blood sugar, and it inhibits xanthine oxidase, which is another superoxide producing enzyme. Now, two things here. One is some people are worried about rhubarb in terms of the source, because it's a source of oxalates. Now, there's only 200 milligrams in it, so there's not a ton. If you are worried about that, PHP makes a great product called Oxalate Scavenger. And so you can take those at the same time, and it contains some calcium, so the oxalates will bind with the calcium there and get excreted rather than cause problems in the body. And also, this supplement, Nostifen, is not designed to be used for long periods of time, a month at the most, probably a couple of weeks. You want to pulse this because this is shutting down parts of the immune system. You don't want to do that for long terms. This is designed to press pause on the production of peroxynitrite, right, and the arginase steal long enough that the nitric oxide synthases can get back on their feet and start working like they were intended. So because of that, we want to do things a little bit differently with this protocol. And so we want to start out with the NOS Defend. Sorry, I've got the wrong name there. It was a previous name, NOS Protect. So it's the NOS Defend and the H2 Infuse, and that will begin to reduce the peroxynitrite levels, reduce the superoxide levels, and reduce the arginine steal. And then you start adding in the NOS Assist on week 2, the Zona, the Berkeley Life, and finally on week 3, add back in the NOS 3 Assist. So you can see that those green boxes represent when you start something. So week 1, start with the NOS Defend and the H2 Infuse. And week 2, then you add in the NOS Assist, the Zona, and the Berkeley Life. And then week 3, you add the NOS 3 Assist. And then you'll see that kind of in week 5, after 4 weeks, and that's the longest I want you to go, you need to take off the NOS Defend, right? Again, I've got the wrong name there, so I apologize. You want to take away the NOS Defend, at least for another month. Let the immune system take care of the viruses, and so forth and so forth. And then if things aren't going the way you want, you can consider bringing it back in. So that's where I put in the yellow boxes. If you want to bring it back in, that's up to your clinical judgment there. Hopefully what you'll find here, and the other thing actually I don't have listed, is the plastic detox. At that point, at the plastic detox, you can add in week 3 as well. So the plastic detox too. And hopefully what can happen there is, as you're getting 8 weeks into this, the Zona plus all the other things are starting to work, and you don't need to support the nitric oxide synthase 3 with the NOS 3 Assist directly. You can take that out. Now, if things aren't working as quickly as you like, you can keep that in as long as you want. There's no need to pulse that. But hopefully you can begin to back down at that point. So to reiterate again, there is our cardiovascular rescue protocol. So we're supporting the physical pathway, the nitrate pathway, as well as all 3 nitric oxide synthase pathways, as well as taking away some of the detrimental effects that are happening around the nitric oxide synthases so they can recover and work properly. All right. So these protocols employ 4 different strategies, and that's to reduce the peroxynitrite and NOS attenuation. Number 2, activate the alternative nitric oxide pathway. So that's a physical pathway and the nitrate pathway. To support the enzymes directly, that's number 3. And then number 4, to support emotional and physical detox, because we know that stress of any type, whether it's a toxin or emotional toxin, is going to affect the body terribly and create extra oxidative stress, as well as reduce the efficiency of nitric oxide production. So with that in mind, I've included a spreadsheet, and I'll figure out, I'm not sure how I'm going to be able to include that here on the video. I'll try to figure that out. If I haven't figured it out, send me an email and I'll email it to you. It gives you different strategies, right? This allows you to customize these protocols for your patient and gives you different ideas on how to do it. So for example, these are some other supplements that Bob has put together and PHP produces that allows you to reduce peroxynitrite. So Peroxy Blocks, I want to highlight that, is a product that Bob has just made. I'll show you the ingredients there in a second. NOS Defend is my formulation. You can see the green blocks there indicate that I've already talked about it. The NOS Activate. SOD Catalate is a great product from PHP. It helps keep the SOD levels so the superoxide doesn't get out of control. And then also some catalase for when the superoxide dismutase breaks down the superoxide into hydrogen peroxide. It also gets broken down. And then NADPH Protect, which is a new supplement from Bob that helps protect the production of NADPH in the body, which is so critical. So I wanted to highlight Peroxy Blocks. It's another great supplement. If you think there's really a lot of inflammation, you can add this in as well. You can see it has a wide range of ingredients there to really come at it from a lot of different angles. It's an excellent, excellent product. Highly recommended. This you can stay on a bit longer than the NOS Defend. I think this can be used a little bit more long term. I don't think it's as directly targeted as a NOS Defend. They really are different products. So strategy 2, activate alternative pathways. Under exercise, you can see there's a picture of Dr. Joseph Mercola. He has an excellent video out there about exercise. I think he calls it the nitric oxide dump, or the nitric oxide exercise. It's a funny video. It's a great exercise to increase nitric oxide. Sunlight will increase nitric oxide level. The Berkeley Life we talked about, Zona. Sauna, heat shock protein activates NOS3. Makes sense, right? So sauna is a great way for bringing up levels of nitric oxide. The third overall strategy is to support the synthase enzymes, and those are the cofactors as well. So supporting glutathione will help keep BH4 in its reduced state. We need the NADPH, and so NADPH assist is a great way to make sure that we're getting an electron donated to the NOS enzymes. We already talked about NOS3 assist, BH4 assist, another PHP product. It's a great product. And Krebs Heme Assist, which is a new product that was put together, I think, by Beth O'Hara in our team. It was either Beth or Emily, and forgive me, I forget which one. So forgive me, guys, if you're listening to this. So we need a healthy heme molecule to be able to make a nitric oxide synthase. So if you have SNPs in your heme pathways, you want to think about this product. And last, our fourth strategy is to support emotional and physical detox. So you can see there's the plastic detox. We all have, remember 93% of us have BPA. You've got BPA in your system. You need to get it out. So if you have hypertension, give this a try. Do a detox for a couple months and see if that doesn't help. I think it will. Adaptogens, I don't have any specific recommendations. You can use your favorite adaptogens with your patients, whether it's ginseng or astragalus, but adaptogens are awesome for modulating the stress response, right? If a person has high glutamate or glutamate problems, a glutamate scavenger is a great way to calm things down and reduce stress levels. Of course, sauna in terms of detox is huge, and there's a ton of different detox supplements out there. I know Genomic Nutrition has a bunch of new ones too, so be sure to check in with them on that. All right. Congratulations, you have successfully completed all 9 steps. So if you're still on this video, you get a gold star. Let me know in the comments that you completed all 9 steps. I just think that's awesome. If you have any questions, there's my info right there. Feel free to text me. I will respond. You can use email, and there's my address there if you do things the old-fashioned and want to send a letter out. And that's me. I'm in central New York is where I'm physically located. So I know there's been a ton of information, but I also know that you've taken away a ton of information from this and that you have some actionable ways to go out there and help people resist and fight the aging process, resist and fight hypertension, and resist and fight cardiovascular disease. It's been a pleasure making this slide, and I look forward to meeting you in reality.